right, so today what I want to do is pull together the topics that we've talked about and also address a survey question that I have for you in the beginning of this class. I asked what topics you were interested in terms of materials, science, engineering, and several of you mentioned you wanted to know how new materials are created. And so I want to pull together the topics we've talked about so far in the class and also answer the question of how new materials are created. And this is through a journal article in Advanced Materials. And the title of the article is, okay, so there's a paper I put into E3 for you to look at. And I wanted to talk to you about how what you've learned can help you understand what this paper is talking about. So a thermoformable boron nitride-based all-ceramic is the title of the paper. It's a brand new material that this group, the research group, has discovered and created. And in this paper, they talk about how they were able to discover it, how they were able to make it. They discuss the material properties and why it behaves the way it does. What is interesting about this new material is that it's thermoformable. So thermoformable means that you can change the shape under heat. So most materials we know, once you have a ceramic material is very hard and brittle. It's not something you can bend, right? The bowls that you have at home made out of ceramic, you can't just heat it up and then bend it into a new shape. Things that can do that are more like organic materials, polymers, metals can be thermoformable. But usually ceramics, no, you cannot do that. So they discover something new and different, that you could take a piece of ceramic material, heat it, and then press it into a new shape. So that's very interesting because now you have a whole new different way of shaping a ceramic material. And so some of the things that they talk about are ceramic matrix composites, or CMCs. Okay, a ceramic matrix composite, a composite is something that we will talk about later on in this class, in the semester, but it's basically a material that's made out of two or more different materials. In a ceramic matrix composite, you have a ceramic backing and a ceramic insert addition to it. So you might have something like this, and these are ceramic fibers, and the backing is a ceramic matrix. In a ceramic material, fracture or failure, and something we will also talk about later on in this class, happens by crack propagation. So if you have a very small crack on the surface of any ceramic material, because the bonds in the ceramic materials are usually covalent, sometimes covalent and ionic, it is very, very strong. So it has a very strong bond. So it's very difficult to break that bond. But once you start to break it, you will get something called crack propagation. So the crack will travel through the material and the entire material will fracture. So that's what you see usually, right? It's very strong, but if you hit it hard, then it shatters in a ceramic material. So by putting ceramic fibers in there, what it does is it slows the growth of the crack. Because instead of the crack going straight through the material, now the crack has to go around the fibers, something like that, before it could go all the way through the material. So it slows down the crack growth, and so it makes the ceramic matrix tougher. It can absorb more energy before it breaks, right? That's, remember, the definition of toughness. Okay, it's the amount of energy a material can absorb before it breaks. So by adding ceramic fibers, you're increasing the toughness of the ceramic. Okay, so that's what they did. They started with a ceramic matrix composite. They're making something, and this invention or this discovery was actually accidental. They didn't mean to develop a thermal formable ceramic. It's not something that most people think can be done, so they weren't thinking about that. They were actually making a ceramic matrix composite for something else, for another application. And so they were making the ceramic matrix composite, and the ceramic particles they were using, so the particles are hexagonal boron nitride. And the matrix is boron oxide. Okay, so that's what they were making. They were making a boron oxide matrix with hexagonal boron nitride particles embedded within. And you know now, based on what we've learned, what hexagonal means. It's referring to its crystal structure for the boron nitride. Okay, so boron, if you look in your periodic table, boron is in the second row of the periodic table, third column. And nitrogen is second row, fifth column. So if you're looking at the periodic table, boron and nitrogen are in the same row. They're separated by an element. Does anyone happen to know what? I don't expect you to have memorized the periodic table, but just in case, do you know what element is between boron and nitrogen? Carbon, very good. So carbon happens to be second row, fourth column. Okay, so having that picture in your mind, what kind of bonding do you think exists between boron and nitrogen? Covalent, right. So it's covalent bonding. Okay, so they share electrons. They don't share it exactly like carbon, but very similarly, right? Because they're so close on the periodic table, they have a lot of similar properties. So definitely the covalent bonding to boron nitride has a little bit of ionic flavor to it because boron and nitrogen don't have exactly the same electronegativity, but they're very similar. So if you were talking about just carbon by itself, then carbon has just purely covalent bonding because carbon to carbon have the same electronegativity, right? Okay. So you can use carbon as a background to think about how boron and nitrogen would behave with each other. Okay. So very similarly to carbon, boron and nitrogen also has a cubic phase and a hexagonal phase. So there's a cubic boron nitrogen phase and then a hexagonal boron nitrogen phase. Does anyone remember what cubic carbon would be? What kind of material would a cubic carbon make? Diamond, right. So a cubic carbon is diamond. Each carbon is bonded to four carbons are bound together, and it is in a diamond carbon in the cubic structure, and it has two overlapping FCC. So for cubic boron nitride, it also has two overlapping FCC. So the cubic boron nitride material is very, very similar to diamond. It has the same crystal structure, is very hard. Okay, in some instances, it's actually preferred for cutting materials, the cutting surface. We talked about how for materials that have very strong bonding, it will have very strong resistance to local deformation, which would make it very, very hard, right? So a cubic boron nitride would be very, very hard and can be used to cut other materials. And in fact, this is usually preferred compared to diamond for cutting steel. So cubic boron nitride powders or coating is usually put onto a cutting tool instead of diamond to cut steel. Can anyone guess why you would want to use boron nitride instead of diamond to cut steel? I don't actually know the cost. Let's assume that the costs are similar. So steel is iron with carbon. So steel, we'll learn more about the different phases of steel after the midterm. But steel basically is an alloy of iron with a little bit of carbon added in. So any ideas why you would not want to use diamond to cut steel? Excellent, right. Because diamond is made out of carbon, and if you're cutting something usually that creates heat, right? And the heat will drive some of that carbon into the steel, or it can, and that will change the concentration of carbon in the steel, which will change the behavior of the steel. So you definitely don't want to be introducing carbon into steel that you cannot control. Okay, you want to be able to control how much carbon you diffuse into a piece of iron to make your steel. Once that's done, then you don't want any more carbon either to come out or to go in. Okay, and so because of this, because of the ability for carbon to dissolve into steel, people use cubic boron nitride to cut steel instead. But we're not using cubic boron nitride, they're using hexagonal boron nitride. So what kind of carbon material would be similar to a hexagonal boron nitride? What is it? Graphite, right. So graphite is hexagonal carbon. So hexagonal boron nitride will be very similar to graphite. They are made of sheets of hexagonal. In a hexagonal boron nitride, you have hexagonal structure, but instead of all the elements being the same, they alternate. It's boron, nitrogen, boron, nitrogen. Okay? And they form these sheets of boron, nitrogen in the hexagonal plane with very strong covalent bonding in the plane of the sheets, but weak van der Waals or secondary bonding in between the sheets, just like graphite, right? So it's easy to shift the sheets, but it's difficult to stretch them because of the strong covalent bonds between boron and nitrogen. And so you could compare the properties of hexagonal boron nitride to kind of like graphite, that it is strong in one direction, but weak in the opposite direction. It has strong bonds, but it also has some ability to have a little bit of electrical transport because they do have some n-bound or delocalized electrons. Not a lot, but a little bit, just like graphite does. Right? Carbon in this shape do not have all of the electrons involved in bonding. There are a few that are delocalized, and therefore that's why graphite can conduct some electricity. Okay, so similarly with hexagonal boron nitride. And then we're going to talk about the term anisotropy. This term means having different properties based on different directions. Anisotropy means that a material behaves differently if you're pushing it from the side versus pushing it from the top and bottom, or from diagonal. So depending on how you're using the material will behave differently based on the direction of forces being applied. So that's a definition of anisotropy. The properties are different depending on different directions. Isotropic materials have the same properties in all directions. So we would expect cubic BN boron nitride to be isotropic and hexagonal boron nitride to be anisotropic because of their crystal structure. Some of the uses for hexagonal boron nitride, besides in this brand new material, is as lubricants in mechanical applications because the layers slide so easily with each other. They're used to lubricate like bearings and things like that so that mechanical parts can move past each other without a lot of friction. Okay, so hexagonal boron nitride is used in lubricants. It is also one of the main ingredients in cosmetics. All different kinds of makeup, like foundation, eyeliner, lipstick, lots of different things have hexagonal boron nitride in it as a material that can cause easy flow of the makeup over your face so that it would slide easily. So it gives it a smooth appearance instead of clumpy appearance. So boron nitride is hexagonal. Boron nitride is used in a lot of makeup. One other thing I want to talk about before we talk about this particular material is something called phonons. Phonons are lattice vibrations. So basically, it is a way of representing heat or thermal energy. So we know that if you have, just a reminder, you have this diagram, energy versus bond length, looks something like that. At your minimum energy state, you have some ideal bond length. As you increase the energy, most of the time you're increasing the energy because you're applying heat. Then the bonds will start to vibrate between these two positions, and the average bond length will increase. So lattice vibrations is another way of talking about thermal energy in the system. And so it's a vibration, so we can represent it in a compressive wave, right, like sound. It's a wave. But just like light, we could talk about light as waves or as particles. So light as waves or as photons. So you could think of phonons as the equivalent to photons. So it's a particle representation of lattice vibration. So that's what phonons are. Okay? So it's another way of looking at lattice vibrations, which in materials is usually thermal energy. And because of the crystal structure of hexagonal boron nitride, phonon transport is anisotropic. So the way phonons can move inside a hexagonal boron nitride is not the same within plane and between planes. So it has different properties. Okay, so those are the things that you need to know about hexagonal boron nitride, which is inside the particles inside the ceramic matrix material. And then the way the ceramic matrix material is made is that the researchers wanted to make something that has a high concentration of hexagonal boron nitride. They actually have 60% of the materials made from hexagonal boron nitride. So what they did is they took these particles of hexagonal boron nitride, they put it in a polymer material. They put it into a polymer material, and then they shook the material so that that energy causes the hexagonal boron nitride to kind of line up so that within this polymer material, the boron nitride is kind of all pointed in the same direction. And there are a lot of them because it occupies 60% of the volume. So they take this boron nitride particle, they put it into a polymer slurry liquid, and then they shook it until everything is all lined up. And then they burnt off the polymer, and then they flow oxygen over this material, and it's replacing the polymer with a boron oxide. So the matrix ends up being B2O3, and this occupies 40% of the volume, and these particles are hexagonal boron nitride, and it occupies 60% of the volume. So there's a lot of particles like packed into that matrix. So this is what they made. They made it for one particular application, but then what they found was that when you heat this material, so boron oxide, it has a melting temperature of 450 degrees Celsius. Melting around 450 degrees Celsius. What they found is that when you take this ceramic matrix composite to 450 or above, it actually doesn't become a liquid, or at least not a liquid that is normal, what you normally see. Okay? it actually becomes a non-Newtonian fluid. So let's talk a little bit about what a non-Newtonian fluid is. So a Newtonian fluid, like water, for example, has a constant viscosity. So usually we talk about the viscosity, how well something flows if we stir it, right? Like water, it's very low viscosity because it's easy to stir. And something like oil has a higher viscosity. You need to put in more force in order to stir it. So you may have, this is a low, the slope is the viscosity. So something with a low viscosity means that you, this is R, and that's shear rate versus shear stress. So that you don't have to add a lot of stress to get a high rate of shearing, of moving the particles in the liquid. This one means that you need to put in more stress. So to get the same shear rate, this material only needs this amount of stress. This material needs a higher amount of stress. So this material has a higher viscosity. Well, it's more difficult to move the particles around. So a Newtonian fluid, viscosity is constant. Okay, a non-Newtonian fluid, the viscosity is not constant. So a non-Newtonian fluid, the viscosity changes with applied stress. How many of you have seen the demonstration or made it yourself with cornstarch and water? Can you raise your hand if you've seen that? Okay, most of you have, right? Okay, so I brought some. In case you haven't seen it, you can open it up. So this is something you can make at home yourself. It's just cornstarch and water. And I'll pass it around so you can all see it. I brought some chopsticks so you can kind of play with it. So it's a liquid, right? You can see it flowing around. But it's only a liquid at very low stresses or no stress. Okay, but if you stab it with a chopstick, so you're putting a lot of force on it, you'll notice that it becomes a solid. So if I move it slowly, it just goes in. But if I stab at it, it doesn't. And you could try, just be careful not to splash yourself, but you could see that if you could pull a big chunk out, and then it becomes a liquid after the force is done. So I'll pass this around. So that's a non-Newtonian fluid. The shear rate changes based on the forces you're applying to it. So why does it do that in cornstarch and water? Is there a name for that in Mandarin? Do you call it something? In English, we call it oobleck. You can make it, so what you would need to do is just get a lot of cornstarch and add a little bit of water at a time. If you add too much water, I'll explain why this works. So cornstarch and water at low stresses, the cornstarch particles, this is cornstarch, they're very small. They're like on the order of 1 micron, 0.001 centimeters or millimeters. And then at low stresses, each of the cornstarch particle is surrounded by water. Okay, the water coats each of the particles. So the particles move past each other. They slide past each other very easily. But when you apply stress, you actually squeeze the water out. You squeeze the water out, and the particles are in touch with each other, and they get stuck. There's friction between the particles, so they kind of get in each other's way, and they don't move as well. Okay, so when you make oobleck, you want to make sure you're not adding too much water, because then you end up having too much water in between the particles, and it's hard to squeeze the water out when you apply stress. Then it doesn't behave as oobleck anymore. So you take cornstarch and you add just a small amount of water, and you kind of mix it until it just is, it's really hard to mix because You try to mix things too fast and it becomes a solid, so you have to be very patient and mix it very, very slowly for it to be like that, okay, to make oobleck. But oobleck is one example of a non-Newtonian fluid. So this is when forces increase, the viscosity also increases. Hexagonal boron nitride is a non-Newtonian fluid, but in the opposite way. When you increase the force, viscosity decreases. Some other popular examples of the materials that behave in this way are ketchup, paint. So when you brush your teeth, the toothpaste you squeeze onto your toothbrush needs to be kind of solid so it doesn't just flow everywhere. But when you brush your teeth, it needs to be able to move around easily, right, and coat your teeth. So that's what toothpaste is a non-Newtonian fluid that viscosity decreases when you apply a force to it. It smears very easily. But when you don't apply any force, it behaves like a solid. Okay? Ketchup is the same way. That's why, sometimes it's really hard to pour ketchup. But if you hit the bottle, you're applying stress to it, then it moves the material. It causes it to flow. Right? So ketchup is the same. Paint also, you want paint to be able to be easily applied to a wall. So when you apply a force, the paint moves very easily and smoothly. But once you stop applying the force, you want the paint not to move because then it'll drip, right? So once you stop applying the force, the paint actually stays on the wall like a semi-solid. Okay, so paint is also a non-Newtonian fluid. So we have lots of things in our lives that are non-Newtonian fluids where the force, as you increase the force, the viscosity decreases. So that's what the hexagonal boron nitride is. It's a non-Newtonian fluid which decreases in viscosity when you increase the force. So that's what they found. They heated this material. The boron oxide melts at 450 degrees. But the material itself doesn't change because it has all this boron nitride inside. Oh, and by the way, the reason why this is the way it is because there are some secondary bonding and entanglement between the particles in this kind of fluid. So that holds it kind of together when you're not applying a force. But when you apply a force, you shift those bonds and those particles and you break the secondary bonds and the particles then can move past each other. Okay, so that's why it works. And same thing with hexagonal boron nitride. When you apply stress to it, you're able to move the layers, the hexagonal layers of the boron nitride past each other, so it flows. So you take this material, you heat it up, it still behaves as a solid. Now you press it. You put some pressure on it, and it will move, it will flow. And so they're able to take a mold of some complex shape, take the boron nitride CMC, apply pressure to that heat, of course, to above 450 degrees C, apply pressure, and cause it to flow over the mold, release the pressure, and now you have a ceramic material that's in this new shape. And in the paper that I shared with you on E3, they show pictures of what they're able to make with this kind of process. And so now you can imagine they can make very thin sheets of this material, and they can make very complicated shapes with a ceramic material, which is usually very, very difficult to do. Ceramic materials usually are not easily cast into difficult, complicated shapes. And so now they could do this, and it could be used in electronics as an insulator over complicated integrated circuits. So it has high insulating properties, but it could also form lots of different complicated shapes. So that's a brand new material that didn't exist before that people were able to make. So they discovered it by accident. They were making this CMC for something else, and then they heated it up and noticed that it actually can be molded when it's in this higher temperature. It doesn't just melt. You can actually form it into different shapes. So very, very interesting. And then so I really encourage you to read this paper. I think you'll find it very interesting. And that you'll also find that it uses a lot of terms that you've learned in this class so far. It talks about material structure and also refers a lot to mechanical properties of this material. So it talks about the strength, the strain, and also resilience that they tested. They tell you what the stress is, the strength is of the material, the resilience of this material, and all sorts of things like that. So you should definitely, I don't expect you to understand everything in the paper, but you should be able to read it and see like, oh, okay, these are terms that we've talked about in this class. This is how it is actually used in a research project and in characterizing new materials. And then I'll see you on Friday.